Welcome to Tomorrow Unveiled, where we explore the cutting edge of science and technology shaping our future. Today, we're digging into something that, well, it affects every single one of us, aging. But not just the ticking clock, right? We're talking about these incredible breakthroughs suggesting we can genuinely influence, maybe even reverse some aspects of how we age.
Exactly. It's really shifting. The latest science isn't just aiming to tack on more years. It's about adding life to those years. Real vitality.
Sustaining our minds, our bodies, keeping that sharpness.
hmm Pushing past those limits we always thought were, just inevitable.
That really is the goal, isn't it? Not just longer, but better. So our dedicated research team has been wading through a ton of new findings in longevity science.
A lot of noise out there sometimes.
Totally. So we've tried to filter that to pull out the really actionable stuff, the insights that seem to be cropping up again and again across different studies.
Yeah, the cross-corroborated findings, that's what we're focusing on.
And we found some truly eye-opening developments. We're going to unpack some revolutionary work in cognitive reversal.
Which is huge.
Huge. And the precision of these new biological aging clocks, pretty amazing stuff there.
Unbelievable.
Plus, some surprising environmental factors, like things you wouldn't expect influencing how fast we age.
And how AI is just turbocharging the whole field.
Okay, let's dive right in. First up, the brain. What if we could do more than just, slow down cognitive decline? What if we could actually reverse some of it? It sounds almost like sci-fi.
It does, but the research team that compiled this information flagged some really unprecedented progress here. It centers on a specific protein called FTL1, that's ferritin light chain 1.
FTL1, okay.
And this protein seems to be a major player in cognitive aging, specifically in the hippocampus.
A memory center.
Right. Exactly, the brain's memory hub. So this protein is right there, impacting learning and memory directly.
So what's it doing? How does FTL1 actually cause that decline?
Well, the details are pretty compelling. In mouse models, aged mouse models reducing FTL1 levels didn't just stop the decline.
Wow.
It actually restored memory function and the proteins needed for synapses, basically back to youthful levels.
Well, a genuine reversal.
A genuine reversal in those models, yes. It seems FTL1 kind of attacks the brain on multiple fronts, It physically damages the neural structures.
Making connections weaker.
Right, and it slows down the energy production in the cells, the metabolism. It's like dimming the lights in your brain cells.
Okay.
And it messes with iron regulation, which leads to oxidative stress. Think of it like cellular rust building up.
Geez, so it's hitting multiple systems at once, not just one thing.
Exactly, a cascade effect.
So what's the big takeaway here for us listening? Thinking about our brain health long term, does this change the game?
I think it really does. The key insight is that FTL1 looks like a really high-value target for therapies because it hits several of these fundamental aging hallmarks simultaneously.
Right, the structure, the energy, the stress.
Yeah. You might only need one intervention targeting FTL1 to get broad benefits for brain health, instead of, juggling 5 different approaches.
Like finding one key lever instead of dozens of little buttons.
Precisely. It shifts the focus from just managing symptoms to potentially fixing the underlying causes.
That is incredibly hopeful. Okay, moving from inside the brain, let's talk about speed. Not just how old we are in years, but how fast our biological clock is ticking. These new tools are getting incredibly precise.
Yeah, this is where epigenetic clocks come in. The research team really highlighted how mature these tools are becoming, especially one called the DunedinPACE clock.
DunedinPACE.
Think of it like a speedometer for your body's aging process.
Okay, I like that, a biological speedometer. How does it work? What's it actually looking at?
It's pretty clever. It looks at chemical tags on your DNA. They're called methylation patterns.
Methylation, okay.
And these patterns change over time, predictably, based on genetics, but also, importantly, your lifestyle and environment. DunedinPACE looks at thousands of these spots to give a dynamic picture of your aging rate.
Not just your age, but how fast you're getting there.
Exactly. And the findings are solid, corroborated across studies. There's a direct statistical link if your epigenetic clock is ticking faster.
Your speedometer reads high.
Right. Then your rate of cognitive decline and even motor decline tends to be faster too.
So it's predictive. It's like an early warning sign for actual real-world problems down the line.
That's the power of it. It acts as an early warning system, potentially flagging people at risk for, say, dementia or mobility issues years before they'd show symptoms.
Oh, yeah.
And for researchers, it's gold. It gives them a measurable outcome. If you test a new anti-aging therapy, you can see, does it actually slow down this clock?
That's a concrete metric.
Right.
But how reliable are they? Can other health issues like, say, having cancer throw off the reading?
That's a crucial question. And the research confirms they're actually quite robust. Even in people with common age-related diseases like cancer, these clocks generally hold up.
Really?
Yeah, except maybe for the very, very aggressive forms of cancer. But for most situations, they remain reliable, which makes them incredibly useful clinically. You can trust the reading for most people.
Okay, that's huge for actually using these things widely. Now,
Totally.
something maybe less obvious. It's not just our genes or lifestyle. Apparently, the environment, even the weather, might be messing with our internal clocks.
Yes, this was another standout finding from the research team's analysis. A direct link between long-term exposure to heat waves and accelerated biological aging.
Wait, seriously? Heat waves can make us age faster biologically.
It's pretty striking. The data showed that for each increase in sort of cumulative heat exposure over time, there was a measurable increase in biological age acceleration according to those clocks we just talked about.
Wow. What's the mechanism thought to be?
It's likely related to increased cellular stress, maybe more DNA damage, problems with mitochondria, the cell's powerhouses. Basically, heat stress seems to push those same aging buttons we see elsewhere.
Okay, but what are the bigger implications here? This sounds like more than just individual biology.
It absolutely is. This really shines a light on environmental justice and longevity. Populations who have less access to things like air conditioning or cool green spaces,
Yeah.
they showed more pronounced aging effects from the heat. It broadens this idea of the exposome. All our environmental exposures combine as a direct factor in how we age.
So things like city planning, access to AC, public health measures, they could actually be longevity interventions.
Potentially, yes. Powerful ones. It shifts some focus from just individual choices, eat right, exercise, to meeting societal solutions, climate resilience, better infrastructure. That could impact aging on a population level.
That is a really profound connection. Puts responsibility on a whole different level.
Right.
We're about halfway through, and it's already been packed with some mind-bending science. If you're finding Tomorrow Unveiled insightful, maybe take a quick sec to like this video. If you're on YouTube, subscribe, hit that notification bell so you don't miss future updates. And if you're listening on Apple Podcasts or Spotify, a rating or review for Tomorrow Unveiled would be amazing. It really does help new people find us.
Absolutely.
Okay, carrying on. The future here isn't just biology, right? It's deeply technological, too. AI, advanced diagnostics, they're changing the game.
Oh, completely. Our sources really detailed how AI is just dramatically speeding up drug discovery. Get this. There's an AI-generated drug candidate, an inhibitor for something called the NLRP3 inflammasome.
Okay.
It's being looked at for Parkinson's. It showed significant motor improvements in mice, and it's already getting close to human clinical trials.
An AI-designed drug, almost ready for humans. That's incredible speed.
It really is. And that's not all. There are also these generative AI models, like one called IPF Precious 3 GPT.
Generative AI, so it creates data.
Exactly. It doesn't just analyze what's there. It can generate new, plausible biological data. This helps researchers figure out the differences between specific diseases, like idiopathic pulmonary fibrosis, and just normal aging. It sparks new hypotheses they can then go test.
Like having a super smart brainstorming partner that never sleeps.
Kind of, yeah.
Yeah.
And on the diagnostic side, the research team flagged these ultra-sensitive proteomic panels. They can achieve attomolar detection.
Attomolar. What does that even mean in practice?
It means they can find and measure proteins that are present in incredibly tiny amounts, like concentrations so low, it's like finding one specific grain of sand on a beach hundreds of miles long.
Wow, that's sensitive. So what does that let us measure?
Things like markers for low-level chronic inflammation and inflammaging, or early signs of neurodegenerative diseases, directly from a blood sample much earlier than before.
Okay, so AI designing drugs, AI generating hypotheses, super sensitive tests. What's the real impact for us, the listener, from all this tech?
It's fundamentally shifting us. We're moving beyond just tracking our current health, the whole quantified self, movement, step counters, heart rate,
Yeah.
towards building really detailed predictive models of our future health, the predictive self.
Predictive self, I like that.
It allows for truly proactive health management. You could potentially intervene based on molecular signals years, maybe decades, before you'd ever feel a symptom.
That is a paradigm shift for prevention. Okay, so with all these discoveries, all this tech, What's actually getting close to reality? What interventions might actually help people, maybe soon?
Well, a lot is still early stage, definitely, but the research team did point to some real translational progress. For instance, therapeutic plasma exchange, or TPE.
TPE.
Yeah, basically cleaning the blood plasma. A human clinical trial showed that TPE, especially when they combined it with intravenous immunoglobulin, could reduce biological age significantly
So,
by an average of 2.6 years, according to those epigenetic clocks we talked about.
whoa, 2.6 years younger biologically. In humans, that's tangible.
It is. It's a concrete example of using these biomarkers to validate an intervention that seems to work in people.
Okay, what else is looking promising?
Well, there's ongoing work with senolytics drugs designed to clear out those old, dysfunctional zombie cells. The stamina study is looking at combinations there.
Right, clearing out the gunk.
Mm-hmm. And some interesting hormonal approaches, too. One study combined oxytocin with something called a TGF inhibitor,
Yeah, okay.
and it extended the remaining lifespan of old male mice by around 73%.
73%, that's huge in mice.
Exactly, in mice. And that brings us to the crucial caution, really.
I was waiting for that. The mouse-to-human gap.
It's critical.
Uh.
Our sources constantly emphasize this. Rigorous human testing is non-negotiable. Things that look amazing in mice, like rapamycin's effects on lifespan, they often don't translate directly to humans, or the effect size is much smaller. So we need what the researchers call measured optimism.
Measured optimism. Be excited, but be realistic and demand human proof.
Precisely.
Okay, but as these things do get closer, even with measured optimism, it forces us to ask some big questions, doesn't it? Beyond the science, the human side, ethical stuff, societal impact.
Oh, absolutely. It moves squarely into the human dimension. Take cognitive enhancement or reversal. If we can do that, who gets access?
Right.
The potential for a cognitive divide is real. These advanced diagnostics, the therapies, they're likely to be expensive, at least initially. Our sources highlight the risk of creating a sort of two-tiered system.
Where extending your health span, your vitality, becomes a luxury good.
That's the concern. Proactive, cutting-edge longevity care accessible only to the wealthy, potentially widening existing health disparities.
That's a serious ethical challenge we need to figure out. And what about safety? We're talking about intervening in fundamental biology here.
Safety has to be paramount. Even things that look good initially might have unforeseen long-term consequences. Our sources stress that thorough long-term safety testing in humans is absolutely critical before anything becomes widespread. We can't rush this.
Got it. Safety first, equity second, or maybe alongside it. Okay, looking ahead then, where does longevity science go next? What are the big trends the research team anticipates?
We're expecting a few key things to accelerate. First, a real push to develop clinical drug candidates based on breakthroughs like that FTL1 protein we discussed. A race to get those into trials.
Okay, turning basic science into actual potential drugs.
Right. Second, generative AI. Expect that to become a standard tool, not just for aging, but across many age-related diseases, helping untangle complex biology.
More AI-driven discovery. Makes sense.
Mm-hmm. And third, something we're calling the exposome-epigenome axis.
Exposome-epigenome axis. Sounds complex.
It basically means combining all that environmental data we talked about, maybe from satellites, maybe personal sensors, with our deep biological data, like epigenetics, genomics, proteomics.
All the UMAX.
Exactly. Feeding all of that into AI models to create incredibly personalized predictions of your individual aging trajectory, considering both your biology and your world.
Wow. That's hyper-personalized. So bringing internal and external factors together.
That's the goal. And finally, expect more partnerships between the companies making these super sensitive diagnostic tests and the clinics actually providing longevity care, offering broader, more sensitive biomarker panels to guide truly personalized prevention strategies.
Moving beyond the annual physical to continuous deep monitoring and proactive tweaks.
That's the direction. It's a fundamental shift.
So wrapping up, this week's updates really seem to crystallize a major shift, don't they? Longevity science is moving fast, from figuring out the basic how and why of aging to precisely measuring it, and now starting to actually manage it. It feels like a transition from reactive medicine fixing problems after they start to really proactive, personalized health span management.
Yeah, I think that's right. We're not just learning to, read the hands on the biological clock anymore. We're starting to figure out how to gently adjust them.
Offering a future where maybe vitality isn't just luck or genetics, but something we can actively cultivate by design.
That's the hope. A future prolonged by design, not just by chance.
A powerful thought indeed. We've covered a ton today. We'd genuinely love to hear what you think about all this. Whether you're watching on YouTube or listening on your favorite podcast app, drop a comment. Let us know your thoughts on this week's immortality update and the future of aging.
Yeah, your feedback really helps.
It does. Thank you so much for joining us on Tomorrow Unveiled. We'll see you next time as we continue to explore the frontiers of what's possible.